Hello everybody, and welcome to part 2 of our videos on the hyperbola. So for this video we're going to start out by taking a look at another example. This time we're given a graph and we want to find the equation of the hyperbola from the given graph. In this case it's clear that our graph is centered at 0, 0. So we just need to figure out what A and B are in order to find our equation. So this distance A is just 2. And the distance out to our focus is C, which is 5. So since we have the relationship that C squared equals A squared plus B squared, that gives us 25 equals 4 plus B squared. In other words, 21 equals B squared. And this graph is horizontal, so that means it has the form x squared over a squared minus y squared over b squared equals 1. Which gives me x squared over 4 minus y squared over 21, which equals 1. All right, well, that's it for that example. Now let's talk about an extremely important application from hyperbolas. So this is sort of the equivalent of a reflecting property for hyperbolas, but it's not a reflecting property. This is really just the definition of the hyperbola, but applied to the travel of sound. So this is a system called LowRAN, long range navigation. If two stations, A and B, are transmitting synchronized radio signals, then a LowRAN receiver in a ship can be used to measure the difference in reception times of the synchronized signals. Since radio signals travel at 186,000 miles per second, one can determine the difference in the distance of the ship's receiver from the two stations. By the definition of the hyperbola, this places your ship on the hyperbola with foci A and B. That's where the transmitters were located. With two pairs of transmitters, the ship's location can be found as the intersection between two hyperbolas. So let's take a look at an example that involves this. Points A and B are 2 miles apart. So since they're 2 miles apart, the sound of an explosion at A was heard 3 seconds before it was heard at B. And we will assume that this particular sound travels at 1100 feet per second. So we're going to try to find the equation of a hyperbola on which the explosion occurred. All right, well, since our sound is in terms of feet, what we're going to do is take our points A and B, and we're going to turn them into feet as well. So let's go ahead and start by just kind of graphing this thing. All right, graph what we know. So we can center this wherever we want, so let's center it at 0, 0, as we usually would do to make things easier for us. So A is here, and B is here. Now A and B are the foci, right? So if we remember the definition of the hyperbola, it says that the difference in the distance of the ship's receiver from the two stations. All right, so those stations, that difference in distances is related to the foci of the hyperbola. So these are our foci. And they are 2 miles apart, but that means the distance here is 1 mile. Or in other words, 5,280 feet. So that tells us that C is 5,280 feet. Now, this information here, the sound of an explosion at A was heard 3 seconds before it was heard at B. That's the key piece of information here. That's the difference in the distance. Well, that's the difference in the times, but we can find the distance from that. So the difference in distances which is also 2a, as we've seen before, is going to be 3 times 1100, right? If it's 3 seconds that go by and the sound is traveling at 1100 feet per second, that is 3 seconds times the 1100 feet per second. Gives me the number of feet, which is 3,300 feet. And if 2a equals 3,300 feet, then a is equal to 1,650 feet. So now we have our value for C, we have our value for A, and to find our equation, we just need the value for B now. So C squared equals A squared plus B squared. So 5,280 squared equals 1,650 squared plus B squared. In other words, 5,280 squared minus 1,650 squared equals B squared. So let's go ahead and tackle this with a calculator. And the result I get for B squared is 25,155,900. And I only need B squared, right? I don't actually need B because I'm writing the equation. And keep in mind that since your foci are at A and B, wherever the vertices are, this is a horizontal hyperbola. So since this is horizontal, that tells us it should be x squared over a squared minus y squared over b squared equals 1. So let's see what a squared is. So this gives me x squared over 2,722,500 minus y squared over 25,155,900 equals 1. All right, and that's the equation of our hyperbola. And obviously in real applications, a computer would handle most of these calculations. And if you had 4 sets of receivers, it would find one hyperbola here, one hyperbola for another, and then it would set them equal to solve for the intersection points. All right, well, let's take a look here at equations of a hyperbola centered at HK. I'm not really going to spend any time on this chart because this is the same thing we've seen every time. The only real difference between the charts is that we now have x minus h and y minus k in place of our original x and y. And everything else just shifts in the natural way it would according to the geometry. So if you're drawing your pictures as you go, you don't really have to think too much about this table. But if you would like to pause and take a moment to copy this down, you are of course welcome to. All right, so find and plot the center, vertices, transverse axis, and asymptotes of the hyperbola and graph it. So our center, well, we have to look at our x. It's x plus 1, so that's negative 1 for the x value. And y is y minus 1, so that's positive 1 for k. So our center is at negative 1, 1. And our value for a is 4, because a squared is 16, and b is 2, since b squared is 4. So now we'll just go ahead and start plotting. All right, so since this is a y squared, this is a vertical hyperbola. And so I'm going to count out a in the vertical direction each way, and then b in the horizontal. That tells me my vertices are at, well, my first vertex is at 0. Oops, that's not right. I forgot that I'm not centered at 0, 0, so let's go ahead and fix that. We're centered at -1, 1. So make sure you actually go to the center that you're at. So -1, 1 is our center. And now we're going to go out a distance of a vertically. So if I go up from -1 to 1, or -1, 1, and I go up 4, that puts me at -1, 5. And if I go down, that's going to put me 1 minus 4. That's going to be -3. So that'll put me down here. So my second vertex is -1, -3. For my minor axis on the fundamental rectangle, I'm going to go out a distance of 2 due to this b here. So I'm going to go out here and draw my fundamental rectangle. Now, when I draw this fundamental rectangle, I can draw my diagonal asymptotes through here. We can see these asymptotes are going to be a little more complicated because they're not centered at 0, 0. So we'll have to think about those carefully a little bit. But let's go ahead and finish graphing the vertex here first, or graphing the hyperbola. So we've graphed the hyperbola this time in the blue. And I would also like to find my foci, so that means I need c. So c squared equals a squared plus b squared. So c squared is 16 plus 4. C squared is 20. C is the square root of 20. Okay, so the square root of 20 is a little bit bigger than 4, but not as big as 5. So we're going a distance a little bit larger than 4 away from our center. So if I go to plot this here, I'm going to get one of my foci at -1, and then I'm going from 1, my y value, plus the distance c, which is the square root of 20. Doesn't work out nicely, but that is it. And I should point out that, if you're doing an online program, working on some online homework, you're probably going to need to write this as 4 times 5. The square root of 4 is 2. So 2 square roots of 5 instead of the square root of 20. But that doesn't matter much to me. Now similarly, when I go to plot my focus down here, I'm going down that distance of c from my center. So that's going to be roughly here. It's going to be negative 1, 1 minus the square root of 20. So I found my vertices, I've plotted them, I found my foci and plotted them, I found my center, and now I've got the asymptotes plotted, but I need to actually figure out what they are. Well, the slope part isn't that hard, so let's just deal with the asymptotes off to the side here. So the asymptotes. Well, let's just kind of reason through this. The slope, well, the rise is my distance up from the center, which is 4, and I go over 2. So the slope is 4 over 2, which is 2. So that's one of the slopes, and the other slope is negative 2. And then each graph is shifted. So just like our hyperbola has shifted to negative 1, 1, our lines have shifted accordingly. So our asymptotes have shifted by that. So the easiest way to plot or figure these out initially is to think of them as, instead of y equals mx, as y minus k equals m times x minus h. And we'll have two different ones because we have two different slopes. So we're going to have, for our asymptotes, y minus 1 equals 2 times x plus 1. That's minus a negative 1. And then we'll have y minus 1 equals negative 2 times x plus 1. And then let's just simplify both of these. This is y minus 1 equals 2x plus 2. In other words, y equals 2x plus 3. And for our other asymptote, this will be y minus 1 equals negative 2x minus 2. And if I add the 1 over, I get y equals negative 2x minus 1. So that's our equations for our asymptotes. All right, well, that's it for this example. Now let's just take a look at the general equation of the hyperbola. So this is similar to our cases for the parabola and the ellipse. We have ax squared plus cy squared plus dx plus ey plus f equals 0. And it's a hyperbola if a times c is negative. That is, neither a nor c is 0 and they have opposite signs. And this should make sense because this is ax squared plus cy squared. And when we do all of our factorization, in order to get the equation of hyperbola, we would need a negative between these terms. So whatever coefficients they have should multiply to where one of them is negative and the other is positive. So let's just find the standard form of the equation for the hyperbola here. It's a little typo. And we've got y squared minus 9x squared minus 4y minus 30x equals 33. And we're just going to start by grouping our y terms together. So y squared minus 4y minus 9x squared minus 30x equals 33. And we'll go ahead and give ourselves a little gap to do our completing the square manipulation. But I have a leading coefficient of negative 9 here with my x squared, so I'm going to factor that out. So I get negative 9 times x squared plus, and 30 divided by 9 will simplify to 10/3 x. And then I'll leave two gaps here. So remember, we always add b over 2. In this case, b is 4 for our y quadratic equation here. So that's going to be 4 over 2 squared, and then we're going to subtract it to compensate. And over here, we're going to have 10 over 3, that's our b, divided by 2. So that's really just 10 over 6 squared. And we're going to add it, and then we're going to subtract it to compensate. So if I factor these terms here, I'm going to skip a little step ahead here because we've done this a couple times now. This is 4 over 2 is 2, right? All squared. When I factor this, I'm going to get y minus 2 all squared. That's this whole trinomial here. And then this is minus 4 over 2 squared. That's minus 4, right? 4 over 2 is 2. Squared is 4. Minus 9 times. And now, when I take a look at this x squared plus 10 over 3x plus 10 over 6 squared, that's going to factor into x plus 10 over 6, or 5/3. Let's simplify that a little. It's 5/3 squared minus, and this 10 over 6 squared is 100 over 36, which I'll simplify a little further momentarily. And this whole thing is equal to 33. Well, it's still a little bit of a mess here, but we can clean it up further. Let's take this -9 and distribute it. So here we have y minus 2 squared minus 4 minus 9 times x plus 5/3 squared plus, and when I take 9 times 100 over 36, 9 over 36 will simplify to 1 over 4. So this is 100 over 4, and we're equal to 33. Well, 100 over 4 is 25. So this is really -4 plus 25, that's 21, and then I need to subtract it from the other side. So 33 minus 21 is going to give us 12. And on the left-hand side, we get left with y minus 2 squared minus 9 times x plus 5/3 squared. Lastly, or at least mostly lastly, we divide each side by 12 to put this in standard form. The only problem here I have is that I'm multiplying by 3/4 instead of dividing, so I'll finish this problem up by just rewriting this slightly as minus x plus 5/3 squared divided by 4/3 instead of multiplying by 3/4, and the whole thing equals 1. So this would be our equation for the hyperbola. I think that's a reasonably challenging problem. The algebra is a little bit tough in that one. Alright, well that's it for hyperbolas, and thank you for watching.